Today we will deal with innovative way to develop some PV components. Yesterday we briefly saw about PVT plus MCP, but here I will give you an overview of what could be done, what has been done, and with some spot on research that we have developed at my lab and at my institute. So, as usual, there is plenty of solar energy, but we don't have so much benefit about that. So we have to make some effort to try to collect and use it as much as possible. So if I look at France, if we cover the surface, the area of France of solar collectors, it will allow to answer to 6 times the world energy consumption, 36 times the world electricity consumption, and 1,400 French electricity consumption need. Of course, it is not possible, but just to have an idea. But it would have been so simple to recover all the surface of PV collectors. And why it has not been done yet? Because there is, of course, some barrier and some issue, challenge. As I mentioned previously in the week, the first one is that finally there is a lot of sun, but the density of this energy is quite weak compared to other resources we have at the surface of the Earth. The weakest density in terms of resource are solar energy. So we can expect to have 1,000 watts per square meter of radiation. If we want to produce a lot, we have to increase the surface, or we have at least to think about concentration, as I told we saw yesterday, because without concentration, we can't reach so high level of temperature, and the energy content finally is poor. Okay, it is the same for the wind compared to the others. So here it is the smallest density of energy, and this is the highest. But of course, you have also here the smallest footprint on environment, and here the highest footprint on environment. Then you have biomass and hydraulics, and then in terms of energy density, of course, you have all the carbonate energy, oil, gas, coal, and the ultimate energy resource in terms of density, some few grams of this resource, so it's nuclear, uranium in particular. Some grams of uranium have a high density in terms of energy. Okay, so it is the first part. Why there is no such solar everywhere? It's because there is other resources that are more dense, and so if you explode them for industrial purpose, it's more efficient in terms of business and economy, and but much more impacting for the environment. Then, from this resource, we need what? We need heat, we need electricity, and then we need, when we have produced this energy, we need to distribute, to transform, to distribute, and to store, and to restitute. Okay, that's so here also an issue for solar energy is to be able to convert. Some conversion are quite energivore, energy consuming in terms of efficiency, and for sure you have to think about storage to deal with the intermittency, night and day, and winter and summer, and when it's cloudy and sunny. Okay, whereas for the other you can produce constantly and the storage is not issue. Then what you need as a final energy, you need it, cool, electricity, and mechanical. And so what is important is that the characteristic time could fit. Whereas, for example, for solar energy, if we want to produce some hydrogen that then will be consumed, the time constant of both producing and consumption are different. For example, if I have a PV central to produce hydrogen with electrolysis, it will spend 6 hours in one day, in a fully sunny day, to produce amount of hydrogen. And whereas when I want to use it, for example, with a fuel cell to produce electricity, it will be consumed in maybe 3 hours. Okay, so sometimes it is longer to produce a resource than to consume. Very often it is the case for everything. Also, it's longer to produce than to consume. Okay, so it's also has to be taken into consideration. And also, what is also important to consider is the scale. Which scale we are considering, massive or small quantities, and reversibility and duality. So it is this context that make also all the issue about the development of solar energy, and of course that we have to try to find solution. But it is not so simple as my first slide to say, yes, there is plenty of sun everywhere, so we should develop that. We have to take in consideration that the density has to be improved, that the time dynamic between production and consumption is different, so that there is also variability and intermittency to deal with, and at what scale we are considering. The advantage of the sun is that we can start from the small scale, local, your house, or solar application, just the domestic heat water for small installation, to big scale. Big scale, it could be a big central, or it's also big integration, massive integration at the scale of a territory, and especially urban territory. So we try to find solutions that will consume less and allow to produce integrated energy. So when I'm starting from the PV, we found some PV central, and especially in a big desert and in area where you can't do anything. Now in Europe it is very controlled. You have the right to develop a big PV central in place where you can't do anything else. That means if you can make, it is a field where you can make agriculture, you can't put PV like this, okay? Or you have to find solutions that PV will protect, will be helpful for the agriculture. For example, it could be a greenhouse with PV, so what we call agriculture PV, agri-PV, okay? But a PV central like this on a field where you can have animals, cattle, agriculture is forbidden. Also, where you can construct house or buildings, it's forbidden, okay? So now, at the time, we find some developments on floating PV, because on lake, we say, okay, we can do, it's okay, we can maybe try to put some floating PV. So there are many developments on this area. Also, in place where it was previously, I don't know how you can say, the rubbish, waste deposit. Okay, so in this field, it is very polluted. You can't imagine to build building because it's too much polluted. You can't also imagine to make agriculture. So for this area, it's allowed to develop some PV integration. Other place where we can't do nothing else, that could be big installation in your point of view. It is a big car park. Car park in cities. When you have a big shopping center, sometimes you have a big car park, and there is now obligation to put shading protection for the car. So that umbrella, PV umbrella. So it could be big surface. Okay, but for other ground where you can do something else, it's forbidden. So it's pushing also to integrate PV, and we will see different way to integrate that. And it has a sense because you can produce locally for a local need. So it's very interesting. So there is still innovation in the way to integrate it as a full components of building, and to use it also for other things like a window, like shading for the sun, like roof part, like tiles. That is what I will show you. If we massively integrate, depending of the country, of course, depending of the source, the sun, we can estimate that we can produce and answer 15 to 60% of the needs at the city scale. So it's interesting, including mobility plus the building. So now there is also more and more coupling between integration in building and try to answer to building needs, but also coupling with mobility and especially electrical vehicle. Okay, so that electrical vehicle that could be considered as a way to store energy when you don't need it, because it's a battery, and if you plug to your building, you can use it. So there is what is considered to be integrated to building. There was a big debate in the beginning of the 2000 years about what is integrated to building, and there was a big push to consider that only was PV is integrated to building if he replace a building envelope or a building element. Okay, so if he becomes a tiles, for example, like this, like you have Sanyo building in Japan, which is fully full of PV, well integrated, we can say, whereas on the right side is not really, it was not really considered to be integrated because it's just put on the roof as a over imposition. Okay, so there is many categories that is considered to be integrated or not. It is one, so on top of existing structure, that not provide a closed covered function. Okay, so you can find all the configuration, juxtaposition the roof, just on a flat roof, on a facade, or shading. The C2 is integration taking part in closed and covered function. So it's a PV, but it is a full, also a completely entire building components. Okay, so tiles, windows, double facade that have a use for light. At the beginning of the 2000s, it was only the integration in a roof south with a good inclination was also supported by subsidies. Okay, it was impossible to think about integration in facade, in east, in west, but now it has changed. And here, for our latitude, the best inclination, if you want to maximize the production of electricity, is 35 degrees in France. Okay, but I don't like if you want to produce the maximum. Now I prefer if you want to produce in order to try to find a solution for your needs. It's better. So now we can play with also the other facade, the other orientation. So if I consider on my house that I am at 35 degrees, it is a reference to produce the maximum in France, so it is 100%. If I put on a facade, I will lose around 30%. Okay, so you see 70%. But the potential of facade is much higher. If you are not in a house, but in a tower, it's much higher. If you are southeast facade, it is a little bit less, but it's not so bad. You are losing 5% more, but you are around 65%. If you are on the roof east, you still have 80%, and west you have also 80%. Okay, so it gives an interesting idea of if we have different orientation, what we can expect compared to the best optimized full production in your place. I like this kind of diagram that give a quick idea regarding the place where you are, to try to find the best integration, but then after to see the impact if you change this orientation. So it could be translated in what we call correction factor for orientation and inclination. And it's easy to identify if you are fully horizontal at east, southeast, and so on. Of course, for the horizontal, whatever the orientation, there is no impact. Okay, you are losing compared to the best inclination south, and so on. But this is a way also to have an idea regarding your building environment, to see the solar potential finally, depending of each facade. So at that time, we try to model that at a city scale with kind of scan, geometric description of the city, and put on each building envelope this kind of factor to have a look and to have an overview of the solar potential at the city scale. Okay. Also including the mask that we have seen yesterday. The mask is very important, so it could lose a lot in terms of performance. It generates, if it is local mask, so just a small shadow on your PV installation can generate mismatch and then difference of operating. Difference of operating is not very good in terms of performance, but also for all the electronic components. So it's very important to clearly estimate this mask. So we have seen how to do it yesterday, and to plot on our evaluation of the rays of the sun in the sky or obstacle, so that if they are far or if they are close, is the same way to plot it. All the tools, of course, are dealing with that. Architectural integration also is a constraint, because if we want to push for massive integration of PV, we have to show architects that everything is possible, because one of the main barriers is architecture. and so to show them that there is various colors that is possible, that you could integrate also in historical building and in mimicking some wood, some stone. You have also natural light, okay? So they don't want, of course, to put some opaque PV panels if they want to play with the light, and there is heating requirements, cooling requirements that have to be done. So, of course, you can't recover all the building of PV, or except if it is semi-transparent. And so you have to take care of visual, thermal, and acoustical aspect. So regarding a very recent PhD that has been defended in my lab, so it is a PhD of Benjamin Riedel, we played with aesthetical. So we have developed a standard PV modules that you can see here. It is made by the CEA at INES. And with that, we were playing with the different color and the originality that we were printing on these PV panels. And so we were mastering each point of the ink, okay? So we were playing with the space between each point and with the color, and with the color red, blue, and green to give the different aspects and to have a far away aspect, okay? When we are close, you see that it is point. When we are far, it looks like fully white, fully blue, and so on. So, of course, the issue for this was to limit the loss of efficiency, okay, and so to optimize the printing with the loss of the color and the loss of efficiency. At the end, we were able to print like if it was a stone, gray, like a stone or wood aspect, or terracotta also. And with this kind of manufacture, so it's printed afterwards. You print with ceramic and then you hit, and it's not move. It's perpetual printing. You can also imagine to make some motif on the facade if you want to draw a big head with PV panels. And so there was interesting results, especially regarding the white. The white is cooler than the classical PV, and and there was also more diffusion after the layer of the printing, and so finally the performance was not so bad. But we were losing some performance depending of the way to print, of the color. As you see, we can reach 45% of loss due to this. But it was interesting to show that everything was also possible afterwards on a real PV panels for integration in some, for example, historical building, cultural heritage building, where you have to develop specific aesthetical aspects. So it was
how this dye is injected there? How this ink dye is injected?
It's a real printer. So it was with a manufacturer printer. You were a big printer, like where you are making the map of some buildings. So you put and the ink was ceramic ink. So he was mastering where you put each dot to print. So and then heating, and then fix it on the. It was very, very interesting. So other kind of integration. So when you have a flat rooftop, this kind of integration is not so aesthetical, but it is at the level of the roof. And what is interesting is that it could be ventilated on both faces, whereas for other kind of integration is delicate, as I mentioned. When it is on the building, there's a face which is delicate to ventilate. We will see what we can do, but here it's ventilated like a normal PV central finally on each side. So the performance are more interesting, and also the access is more also easy for the maintenance that it is if it is fully integrated in the roof, for example. Okay, the problem that you can have, it is that you can also make some hole in existing étanchéité, waterproof layer. So there was a lot at the beginning, a lot of damage like this, because people were just making hole, fix the PV, and there was many leak after, and so problem of insurance and so on and so on. But now it's much more mastering. Here some PV, fully PV integrated as aesthetical, so it is a full component of building. It replaces the tiles. We have developed with Imeris company also integration of PV on the tiles. It was interesting results, because there was inertia due to the tiles, to the terracotta, and so during the day, when the temperature in summer was increasing, these PV modules were more inertial, and so there was a delay between the peak in the afternoon. For example, the hottest time in the afternoon was 4 o'clock in the afternoon, whereas the hottest temperature of the PV panels was 5 o'clock in the afternoon, almost, so when the temperature outside was decreasing. So it was interesting to add thermal mass. It's like if you had finally a kind of phase change material at the backside. Of course, there's one thing that has been corrected after, that we can see on the picture, and it's not good. What do you see in the picture? Shadow, self-shadow. So then after we put the sails on also on the inclined part, and the tiles were flat. Okay, but it was the first attempt. So they're self-shadow, so it's not good. Okay. So other way to integrate, you get rid of the tiles, and sorry, there's some French, but you can guess that it is to put some waterproof layer at the back side. Okay, integrated as a glazing. So I showed you yesterday my green and pink double facade. So we were working with the company that have then used it to to build the Cité de la Voile of Eric Tabarly. So it's the same principle of the facade that I showed you yesterday, playing with the color and playing with the density of the cell. Okay, so the company was Total Energy at the time. Now it became Total Energies, and the architect was Jacques Ferrier. So it was a result of what we had developed together to show that everything was possible in terms of density, color, and so it was happy. There is also another integration like on the railway station, you can see. Okay. You can have the same kind of thing in a facade. So you can just plug over the facade, it is superimposition, or you can have also some structures that are independent of the existing building. On the facade that I showed you yesterday, they were self-porting. So they were independent of the house. You see, there was a house and the facade. The structure that has been built in aluminium was autonomous in terms of mechanical strength, because it is important if you want to add an existing building. Usually, an existing building, the structure has not been designed to accept a new weight, and a PV module could be very heavy because it is glass. Okay. Also, integration as a sunshade. So this is considered to be a full component of the building because it helps to protect from the sun during summertime. Here also you see an existing building in the south of France. It was a historical building, and the architects had a double skin facade, PV ventilated facade. So it was helping, I will show you the operating configuration, for winter to recover heat in the air gap, okay, and for summer to use it as a natural ventilation system connected to the ground, because under this building there is a cave and it's cool air. So during summer there is chimney effect, and so the cool air is going inside the building. Okay, so the main guide that you want to develop BIPV is to be cautious of the operating temperature, as we insist, and to find solution in order to avoid too much increase of temperature of the PV panels, because of the dependency of this conversion. Is also to try to highlight and to enhance and to recover a part of solar energy which is not used for electrical conversion. So how to use part which is thermal part, it could be interesting. So I show already use a two-way. That more active way is to master the fluid circulation, okay, a calorific fluid that could be water, oil, or water, oil, or air, or a passive way, where you just try to find solution that passively will allow to decrease the temperature of the components. And the best is natural ventilation. So to try to find or time siphon phenomena to find natural circulation. The components so that we have developed, I show you the double skin facade on the greenhouse. We have developed for existing office building. Also facade, you can see that it is not completely flat because the orientation was not optimized. It was not a south facade, it was a southeast facade. So we developed components that allow to give to the PV panels a good orientation. Of course, in the other side, it allows the light to cross. You can't put PV panels on both sides because it will not be optimized, and it will create a self-shadow effect. Also at some
southeast orientation. Why southeast orientation?
Because it was an existing building. We want to demonstrate that one of constraints of the existing building is that the structure are not really designed to accept a new weight, and also that the orientation have been chosen long time ago, and you can't turn the. So we want to show that even the facade was not fully south, there is some adaptation, nice aesthetical adaptation that could allow to optimize the orientation of the PV. We went also on solar steel, so it was to integrate on steel for application in industrial building or stadium, big stadium near Lyon that have these PV panels. We've also Umicore, which is zinc. You know in English comment on dit zinc. It's not iron, it's zinc. All the roofs in Paris are in zinc, and they wanted to develop such a kind of component for putting on a roof, but it was forbidden by the city of Paris by aesthetical aspect, heritage aspect, and at the backside we were using ventilation of air and recover air for the building need. So for the prototype that we are developing, we are not manufacturing the cells, but we are able, especially in collaboration at INES with the CEA, to manufacture PV module. PV cells is delicate. The CEA is developing some PV cells, but we have no skills on this scale, except some maybe some thin film that could bring something in like photonics properties, but we don't at that time work on this scale. We are working more than on the design of the PV modules and adaptation to the final configuration. So I show you this, but I didn't focus. On this one I will focus later. So the way we have designed the heat exchanger and the coupling with the PV cells. So before going to more active operating condition, I will go on the ventilation and what we have done on this. So first, now we are developing building envelope, so that include ventilation, natural or controlled ventilation, that are active in the way that they are producing some energy, and multifunctional that they could also evolve depending of the building needs and of the climate. So we don't work on just passive neutral components. Okay, so we want that these components provide combined function as insulation, preheating or pre-cooling, heat energy storage, electricity generation. Okay. So is the main configuration that we have studied. So Pareto dynamic wall. So with ventilation, with an air gap which is ventilated. Also, we have worked with Pareto dynamic windows. So it's specific windows that allow to an air inlet by specific path. You can see there is free glass. The inlet of air is here, going down, turning and going inside. This kind of windows is interesting to recover a part of it during winter time, because winter time when it's cold outside, the more deperditive component is the window. And thanks to this air pass, the heat which is going from inside to outside is partially recovered. So and it is interesting when you have only one flux mechanical ventilation. So the principle is during winter time you will the more simple is to use it as a double glass finally. So there is an air gap, it is closed, there is watertight, it used as insulation. The other thing is to have a more active mode, that to use this air gap as a way to preheat the air. So you can have opaque PV wall, then the building envelope, and you ventilate this air gap to recover part of it. That could be coupled to the heat exchanger for winter time or to heat pump, because you increase a bit the inlet air. You can use it during summertime as a free ventilation system. So if you're on the south facade, you close the bottom, you open the top, and you allow the air to go from inside the building to outside the building. And in principle, the fresh air which is coming from the north is cooler, and it will allow to cool the building because it's cooler, and also by convection. You can also combine, it was a historical building that has been refurbished that I showed to you, with a path of air going underground where the air is more cool. So it could be Canadian wheel or so. Finally, you are decreasing the temperature of air because there is a path underground before going in the envelope or in the building. But so it's to use it as a natural ventilation system, playing with the chimney effect due to this. This has been developed in a very hot country like Iran. I'm sure in India also solar chimney or wind catcher to enhance natural ventilation when there was no mechanical possibility. So we work a lot on this chimney that allow to cool the building during the summer and to bring some heat during winter. I think you know all this. We didn't work really on this. It is a solar wall. So it is a perforated steel skin. Have you seen that? So the first skin is a micro-perforated steel skin, black, okay? And so the air is going inside the air gap all along the facade. And so is heated, and this air is then injected in the building, okay? Of course, you have to add some filter. So it's solar wall that has been developed by the company Solar Wall, which is a Canadian company. So it's like an uncovered solar thermal collector, okay? Uncovered solar flat plate collector, but the originality is that the absorber is micro-perforated, okay? So the inlet of the air is all along the facade. So it's worked well for the preheating, and it is the reason why it has been developed by Canadian, because some few degree during winter when it's very, very cold, it's important. But the function in terms of refresh potential has not really been studied. There was some attempt about such a collector to use it at a reverse way during the night in summertime and to enhance the radiation exchange with the volt, Celeste volt. Okay, so if the building is hot, you blow the air and through this double skin envelope, and you can this black body can emit radiation with the Celeste volt and cool down the air. But it has not been very well studied yet. For this performance, we can win between 5 or 25 degrees, depending, of course, of the sun and of the temperature outside. So it's interesting. This is on a building in the University of Lyon, where I was previously. So it is the aspect of a real solar wall. It has been installed for practical lecture for the student, and also, see at the backside, it's a big industrial building where there are all the practical work of the students. There is a different energy system and so on, and so it was used during winter time to heat this building. So the target of such components is more tertiary building, office building, commercial, agriculture also could be interesting if you want to maintain a certain level of temperature in a big space, and it's quite robust. So this is the configuration that has been here. It was on 2 floors, and there was it was directly coupled to the HVAC system. So then you can upgrade if it's not enough by a heat pump before blowing in the building. Other system, it is a trombe wall, so there is many development about this. At the beginning, the idea was quite simple. Trombe was living in the Pyrenees, so where there is a big furnace I show you. In the same area, he was working on solar energy. He has a big house made with big stone, so very huge thermal mass. But it was very hard to heat this house because of the thermal mass, and it is very cold area during winter time. And so he tried to put a glass in front of all the wall, and he has seen, yes, that greenhouse effect was very interesting. The stone was very hot. So he said, "Oh, I will make some hole in my wall and put this glass." And he use it to preheat, to heat the house. And at the back, and the stone of the wall of his house were finally storing the heat during the day and release the heat inside the building during the night. Because at that time, such a house, it's a typical house, it's only stone. There is no insulation. So finally, during the day, the sun was impacting the stone. Thanks to the greenhouse, this temperature was increasing. And the time that the heat was going inside the house, it was the night. So it was, so since that time, there was many development of the principle. You can put phase change materials at the backside to store the energy instead of big. There was some tunnels, some barrack of water instead of stone, and many. It's a very interesting principle and simple principle that could be adapted on each a lot of configuration. So the principle of the operating is that you have all, of course, on your in your house. So it is your the main building envelope. Okay, you put a glass. Okay, and you make it possible to play with the opening here, 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 here. Okay, so the classical one is the windows which is not moving, a glass which is not moving, and so during the day he was opening, so there was a chimney effect and circulation, a free circulation. Usually the cool air is down, so going inside, warming and going inside by thermosiphon effect. But then, so it is the main trombe wall, originally a trombe wall. There is protection, of course, for summer, because for summer, if you don't protect, or at least you have to erase the glass because it will be too hot. Okay, so you have to add shading protection for summer. So this is the house. So you see how it looks like. Just had some windows on the house. The optimum, and you see the shading also. The shading at the top for the summertime. So when the sun is very high in the sky. So in terms of characteristics, the optimum orientation is south. It has to be at the backside EV materials or phase change materials. The air gap is around 3 to 6 centimeters, and the inner wall was at that time 30 centimeters of stone. Double glazing is better, that you lose less some energy. The performance is quite good and could cover for such a facade. You see, the facade is important compared to the house. 70 to 85% of the heating need without mechanical assistance. It's fully natural, and the wall can reach 65 degrees. So it was the stone was quite high. The evolution of this, so it's a zigzag solar wall that you can find with a different section and different orientation. So you can see southwest, southwest, and different composition if you want to store or not. So there was one southeast glass section to promote heat and light. So it's a mix with what I showed to you. In one side you have the PV, in the other side you have the glass, in order to allow light to come and to optimize the sun collect and sun use in the south. So interesting also study. This also, instead of stone, there is some container of water. You can see different picture in the 80s. They try to integrate inside also the house a container of water, more or less integrated in the house like a column, to add some thermal inertia. You have collectors with PCM, so I mentioned. Instead of big stone or heavy materials, you can add phase change materials combined with semi-transparent PV. So, for example, here this system that has been really implemented, they were using hydrated salt, and so of course the key element is to choose the phase change temperature of these materials in order to optimize the operating configuration at that time it was for winter, so to recover as much as possible heat. So after you can find with combination of thermocirculation, control inside the building envelope, integration of ventilation inside. Okay. So one of the key elements of such a facade, to recover part of heat during winter, there is many configuration with EV materials, and for sure it will be mechanically ventilated if you want to increase the efficiency. Like this you control the air velocity. When you want to use it during summertime, it's more delicate because you want to use this kind of element as a chimney, a natural chimney, natural ventilation system. And the natural ventilation system is very dependent of external and internal conditions. If you have wind on a building, you have some facades that are in surpressure, some other facades that are under pressure. You can also have wind that is going in your facade and go at the top of the facade and go down, so that you want to avoid that. You want your facade to be a chimney. So wind and natural ventilation is complicated, so you have to know very well your environment, where and what are the dominant wind. And also you have the thermal aspects, because the chimney effect, you have only two ways to naturally ventilate it, is to use difference of pressure, so to use the wind, which is very strong, and to use the difference of temperature with height, so the difference of density. It's the only two natural engine of the ventilation is difference of pressure or difference of temperature. And if there is a fight between difference of pressure and difference of temperature, it is the wind that will win. Okay, the wind is much stronger than difference of temperature and air movement induced by difference of density. So it's complex. It's complex to design, and also to find solution in order to be sure that there is a good enhancement and heat transfer in such configuration. So we implement that, I told you, for both, because we wanted during summertime that the air is coming from the bottom and be extracted from the top. Okay, so of course we have to be sure that for example, especially here, that there is no local dominant wind that is in the other direction, because all that you are expecting by natural ventilation due to chimney effect could be completely neutralized by dominant wind that will come and blow inside. Okay. So it was not the case, hopefully, and so we have made some experimentation to look at. So what we saw that, of course, the density of the sail have a big impact, because it's allowed to hit the first facade or to hit the second facade. So you have finally a kind of ventilated air channel with double flux, with a double wall that are partially heated in one and partially heated in the other. And we find it was good to have a asymmetrical heating of the first facade and the second one. That we find that it was allowing to generate turbulence, and so to improve heat transfer in the air gap. We have also done that for the natural ventilation of this facade, so in this existing building, which is an office building of one of the partner.
But anyway, these channels are like fixed. No air can enter.
What?
This channel, natural ventilation, only some selected holes will be there through which air will be circulating.
No, at the beginning we didn't select the density in order to have the best ventilation. We just select the density of the cell in order for summertime to protect, to identify where the more irradiate zone to protect the house. But then after, yes, the air is during summertime could come at the bottom and could be extracted here. And we find that thanks to the non-symmetry between the two walls, the glass wall and the wall of the house, there was some part more heated on the wall envelope of the house, more heated on the glass wall, and it was good in terms of development of turbulence inside. So it's a facade that we hadn't instrumented, and we try.
Is there any calculations like when you say this non-homogeneity of the cells, and then we need micro inverters?
Yes.
Micro inverters.
It was micro inverters.
So every module you need micro inverter.
Yes, for sure. Yes, because the density is different. So for all this installation, there was one micro inverter per module.
Then it should be very costly.
Yes, but it was research. So, no, and the partner, one partner was a PV manufacturer. So it was interesting to see. It was quite new at that time, the microinverter. So it was interesting to test that for itself. One was an architect. He was interesting to show that we can play with the color and the density. One was Technal. So he's an aluminium manufacturer. So he was interesting to develop. What I told is that we wanted. This is experimental house of EDF. What we wanted to show also that we can integrate PV like this, which is quite enormous, without new constraint on the house. So it's self-mechanical independent. We didn't have weight on the house. So the manufacturer of aluminium frame was interesting to develop such a system to show that it was mechanically independent, stable. So every partner want to test new things, so they didn't look at the cost. It was very lucky. Yes, yes, it was.
Has their own
yes, their own objective in the wool project. Yes, it was interesting. So here it is. Some results, because we have made some experiments on the facade, for example. So it is result presented on the shape of a carpet plot. That means that for every day we were plotting hour per hour the velocity, for example, the irradiation. Okay, so we made a lot of carpet plot like this. So each ray is 1 day with many different data. Okay, like this you can see where is the winter easily. Here it is the flux which is received at different level of the facade. So you can see where is the winter, where is the summer, and there is some problem that we have identified. The facade was in Toulouse, not where we are. So here, for example, interseasonal problem. So it's between winter and summer. There was so we investigate such a thing. So we try to model also the double skin and also to evaluate the temperature. So this is the temperature of the PV facade and try to recover. So finally we find quite satisfactory model that could give the evaluation of the temperature of such components. So it was a mix between physical and data. At the time we didn't we were not speaking about data deep learning, but it was yes, extracted from the same kind of approach. We were also it was also easy to identify the problem. One of the problems that after we implemented the facade, they put some trees, small trees, and we were not aware about that. But when we were analyzing the data, it's at the bottom of the facade seems to have a problem. We don't know why. Maybe it is a sensor which is not good, and we didn't understand. There was a change in the behavior at the bottom of the facade. And finally, for a meeting, we went in place and we saw that at the bottom of the facade there was a tree that has leaf, and there was every day for a few hours shadow at the bottom of the facade. And we were trying to model that. We don't know why it's like this at the bottom of the facade. So this kind of diagram is very easy to identify if there is some problem or not. Okay, so I will not go deeply, but of course we wanted to be as closest numerically and experimental data. It is so we have developed quite also simple model because first was fluid dynamics model, simple model that could allow to manage this double facade and the air ventilation. So it's a simple analogy zonal approach, and we were considering 3 main levels in the facade. It was a PhD also. If you are interested, it's in English because it was one of my PhD that was work on this modelization. Of course, when it was mechanically ventilated, the results were very good, and when it was natural ventilation, the results were very delicate, especially when there is some wind. It's difficult to take in consideration the impact of the wind. So it has been developed in Terenzis and give so with natural ventilation, it is this kind of equation so that provide that has been developed by Brinkworth that provide the evaluation of the mass flow rate, M, air mass flow rate. It was quite good in stable condition. As soon as there was wind, even a small velocity, it was very complicated. But in some stable conditions, so sunny, without wind, it was quite good. Okay, and also when the solar radiation was low, it's delicate. When you have a low solar radiation, it's delicate to have an exact. It's better when you have big solar radiation. The phenomena are very strong, so you are more accurate in your prediction. When the value are small, it's delicate, but it was good at the end. So here you can see with evaluation when there is wind, there is different results. It was a problem. Okay. Other kind, so that we don't develop that, other kind of PV, BIPVT hybrid integrated. So it's a mix with finally the solar wall that I showed you previously. You can see the inlet in between the PV modules and PV facade. So it's also interesting. They were playing with the protuberance in order to generate turbulence and increase heat transfer. It was an interesting study. So you see here the products that could be considered to be well integrated, especially in the right side. And they were playing also about the distribution. Okay, so for the efficiency of hybrid PVT, I will not spend time because we have seen yesterday the thermal and exergy efficiency. We can also, if it is coupled to a heat pump, try to combine the performance coefficient and the heat pump also coefficient. So this is some attempt to combine both. So
this is fluid is air, right?
Yes.
Fluid is air.
Yes, with air. I'm still with air at that time. Yes. So interesting. Okay. Yes, of course, for ventilated facade, the mass flow rate is important for the efficiency. Okay, like we saw yesterday, the flow rate of the water is very important for efficiency of PV cell, but less for the thermal efficiency. So depending of the mass flow rate, of course, the more the ventilation is high, the more the efficiency of electrical function is high, but the efficiency of thermal is low because you can't increase too much the temperature on the air. Another ventilated facade roof that we have developed in real application, it is on the framework of Horizon PV, so it is an industrial wine storehouse. So it was interesting, not because of the wine, but about the characteristic of the building. We want to develop an installation that could produce massively electricity. So because to use an big industrial structure roof, it's interesting, and also try to answer to a part of the needs of the building. What were the needs of the building? So the building was mainly composed of tank of wine. Okay, so very heavy. The building is has a big thermal mass. Okay. It is on the south of France, so during summer they need to cool. So the PV was using to use classical cooling system. Okay, but during winter, the temperature has to be between 14 to 18 degrees inside, and so we said 14 to 18 degrees. It should be possible to reach that without heating system, but just recovering the heat under the PV panels. Okay, and so the development was, so the constraint was the roof slope was not important, only 1%. So we decided to put on both sides of the roof. Okay. The tank side, so inside is very important, so very inert. So not all the roof has been designed to recover the heat. Okay, so we've made some computation in order to evaluate the size, the surface of the roof that we need to be hybrid, photovoltaic thermal. Okay, so I don't know where it is. So there was, finally it was 50% PV, so only PV, not ventilated, and 50% of PVT. Okay, of course we designed the also inverter. There was 3 inverter depending of the specificity of the installation. 3 inverter for PVT and 3 inverter for PV, so 6 at the top. The thing that we have developed is an integration of the PV module, so through this aluminum frame. So the PV module were fixed on this aluminum frame. So there was air inlet and going through the PV. So the ventilation was between PV and aluminum frame. Okay? And so it was tight, airtight. So when we put the PV panels, there was air tightness around the PV panel. So it was a ventilated channel. In one side it was PV panels, and in the other side it was aluminum. Okay. So of course you need to develop also the ventilation tubes. So here you can see the ventilation system. So to recover at each row the treated air. Okay. Then this air was directly blown inside the building during winter time. Okay. What to do with that during summertime? So the idea was to continue to use this heat during summertime, and the needs they have during summertime, so to cool because they have to maintain the wine at a specific temperature, but also to clean. So the big tank during summertime they were putting the wine in bottle, so they empty the tank, the big tank, and so they need hot water to clean after when it is free of wine. So we had on this design a heat exchanger, which is not so common, between air and water. Usually it is the other way. You use hot water and exchange on the air. Here it was to exchange, use the air and exchange on the water. So it's not so good in terms of heat capacity of air, but the quantity of air was massive. Okay. And thanks to that, to produce hot water during summertime, that could be used for cleaning. Okay. So finally, this installation was also designed to work and operate the same way, summer and winter. But summer, we were not using the hot air for heating the building, but for heating some water.
Is this a PCM or?
No, the tank? No, it was a big tank of water. No, yes, because there are a lot of place in this building.
Insulated tank, yeah.
Yes.
What's the temperature there?
60, we were reaching 60 in the tank with only hot air.
And there they use PVT?
Yes, we were using this system of PVT winter and summer. But so winter, the collected hot air was directly injected in the building because it was enough to maintain the temperature between 14 and 80. Okay, preheat, but it was enough. And during summer, the hot air was oriented to a heat exchanger with water, which is not not so common to use air to heat the water. But regarding the surface and the flow rate was important. It was enough to heat the water at 60 degrees. That was enough also for them to clean the tank.
heat exchange is taking place from air to then water.
Yes.
We are losing a lot of, because this side is air side, heat transfer coefficient is very weak.
Yes, that's what I was telling, that it's not so good because air capacity is not good compared to water, but the quantity of hot air was important and was enough for producing the water. Yes, we never saw heat exchanger like this. But the idea was for them to be autonomous in energy and no need of energy. So even if it was not so efficient, at least we could use the system also for summertime to heat this.
Clean the bottles.
Yes, to clean the tank. I don't know what time is it. I have time or?
30 minutes. We have 30 minutes.
I have 30 minutes again? Okay, good. Okay, so we have developed also a model, the same approach. So this is a cut in the channel of the hybrid PVT. So here you can see the roof. There was insulated roof. Okay, there was iron, and as it is an industrial building, so insulation. Then there was the air gap. There was aluminium frame, and the air was going inside here between PV and aluminium frame. Okay, so the airflow was here. If I'm coming back, you see there is an air gap down here, because we couldn't be fully on the roof. So it's only fixed here on the side. There's an air gap which is not used between insulation and the wall, and the air is going between aluminum frame and PV modules. Okay, so insulation with air gap which is not used, and the hot air is circulating here. So it has been implemented on Terenzis also, and for each row and each zone coupled to the ondular and inverter and things like this to model the whole installation. So we found that there was around 10 degrees of difference. So to remind you, half of the roof is fully PV, not PVT, and half of the roof is PVT. Okay, so it was also possible to compare in the same condition the impact of the ventilation on the PV. And so we find that there was maximum 10 degrees of difference between PV and PVT, and so better production of electricity. Sorry, it's in French. I have left some pause, but it's classical numerical and experimental comparison. It was interesting to compare with the PV, simple PV, in the same installation. So we found that it was not so bad. We were able to evaluate what was recovered. What was delicate in this area, it is in the south of France, and it is very windy, very, very windy. So when there was wind, it was also delicate at the beginning to find the results. And you see, it's very, very windy. It's along the Rhone River, so the roof was fully ventilated, of course, because it's at the top of the building. So the impact was important. Okay. Well, this is classical results. So the flow rate at the heat exchanger, to give you an idea, was 2,500 cubic meter per hour. and we had a minimal temperature of 27 degrees. So when it was not a good day, because the grid natural fresh water is at 15 degrees. So the more pessimist day, we could only hit the water temperature at 27. But the optimist day, we could reach 60 degrees. Okay. Okay. So we made different parametric studies on this. One thing for such a ventilated envelope, which is important, is the fire. Okay, and especially when it is vertical envelope. Also we work on the way to find solution. For example, for the facade at Technal, the aluminium office, we find solution in order to avoid, if there is some fire, the development of the fire all along the building finally, because if you want to enhance the chimney effect for sun, if there is a fire, you will enhance the chimney effect for fire. Okay. So we also design something that will, in terms of fire, could contribute to stop the fire or to cut the airflow. So this has some separator. We have tested some separators that could close between each floor. We were also thinking, but we didn't develop that some things that could open the double skin, so leave air crossing the PV facade. Okay, like this, if you leave air crossing the PV facade, it's neutralize the chimney effect. Okay, so we don't develop that, but it could be a solution. Or we tested also some sprinkles, so springer. So you put also injection of particles of water, which was not so bad. So we tested two things: mechanical that close the chimney and sprinkle, to be sure that it could be also developed in a real building where there is inhabitant. But it is important when you are focusing on chimney effect to deal with that problem, to think about that problem when there is a fire. In terms of new development now, so what I showed to you until now, it is aesthetical innovation. It is ventilated facade that could have a function for winter, so heating need, a function for summer for cooling needs. Okay, natural ventilation. We try to develop things that now can evolve by themselves. So also that combined with properties that could also change. Okay, at the time it is the operating configurations that were changing, but not the properties. Okay, so we try to develop new kind of components that have properties that can change. So this is not us, but it is some application. Here, if you can see that kind of, so it looks like air balloon. Or so, for example, this is a good insulation. When it's like this, it is a good insulation. If you, during summertime, you want to get rid of this big coating that keeps the heat inside, you can imagine to unflatted this balloon. And like this, there is no more insulation. Okay, so it is a principle of finally a facade that could have properties which is changing. Could be a very good insulation, and if you get rid of air, no more insulation. So we try to find something like this. So things that could allow sometimes to leave. So it is still my double facade or my double. So can leave all the solar energy crossing the double skin, or can become opaque in one. Could become opaque in one and collect the solar energy, or could become opaque in both and just hit the hair, or become opaque and inert.
It's earthquake. You got.
Sorry?
It's earthquake.
What?
Earthquake.
Yes. What was earthquake?
You experienced this?
Ah.
Just now, there is earthquake.
Ah, okay. I continue?
Yes.
So, or it could be non-uniform in one side, partially, fully. Okay, this is, it could be used naturally or mechanically, and so different configurations. So, with thermal and PV, we can imagine to do that. So changing the properties, optical properties, changing thermal mass insulation properties, changing transmission properties. So in order to be able to finally evolve, to have evolving components. Okay. So for this, we try to look at in the nature. In living organisms, what are the mechanisms that could be useful to implement in the facade? So Kita is well aware of this. So for example, and what we find interesting is two things, insect or plant. Because finally, if you look at this building, and if you look at the insect, they have a common point. What is the common point between this building and an insect? Is that the insect has exoskeleton, and the building has an exoskeleton. The insect, mechanical property of the insect is the envelope, like the building. And so how he managed to deal with all the things, all the exchange with the environment through its envelope. Okay? And so through the envelope, so we call that cuticle, okay? Is breathing. The insect is breathing through his cuticle. He has some hole all over his cuticle, and he has no, how do you call the poumon? What is allow you to breathe?
Lung and heart.
Lung. He has no lung. It's just by natural ventilation. All around the insect envelope, there is different pressure. Okay, in a building, in this facade you will have maybe surpressure, and the other for sure you will have under pressure. Okay, this is the same for the insect. So all is managed by natural ventilation because of the difference of pressure all along his cuticle. He has no heart also. He has a different way to make the blood circulation. So finally, and it's the same for the plant. the plant interface, so the cuticle of leaf, are managing everything. They manage some water exchange. Of course, the insect also is managing the water because it will be fully dry when it's hot. So it's managing the water, it's breathing, and you have a lot of different particles that could be cross or can be filtered. You find also that in hot country, when you have a zoom on the leaf, you will find something like this, and it will induce turbulence when there is wind in order to cool down the leaf. Okay, in some other place you will have a kind of small water tank at the surface in order to manage water when there is matter, not water. So you have also a lot of different optical properties. In hot country, they have to protect against UV. Okay, so it's UV reflecting. It's a protection of the cuticle. The butterfly wing for insect has beautiful optical properties. It's incredible. As I mentioned to you, the anti-reflective coating on the PV cells is made like the wing of butterfly. It is powder, and what is changing in terms of color, it is just the weakness of the powder layer. Okay, because there is interference with wavelengths that give the color, but just is the same materials, but just playing with the witness, it will interact with another wavelength and give another color. Okay, but it's more complex than that for the butterfly. The optical properties are changing a lot with the direction of the radiation. You can have radiation coming perpendicular to the butterfly wing and have high emissivity, for example. And when you are 60 degrees, you have no more emissivity. And all the properties are changing like this with the angle. So we find that it is not for solar energy. It is to be protected in the nature, is to be protected. And so we find that it is to be protected from the birds. When he is flying, there is a double protection. He has a random flight. The butterfly is doing like this. And so this random fly, plus the fact that the wings are moving, the optical properties keep on changing. And the assumption is that sometimes the butterfly can be seen by the bird, sometimes not. Disappear, appear, disappear, appear, and with a random fly. So we think that it is for protection against attack of birds. But optical properties are incredible. And we don't use that for building. For example, we can imagine for winter, when the radiation is quite perpendicular to the facade, that it will absorb maximum, have a big absorption. For summer, when the incidence angle is bigger, it will reflect with the same materials. So this is kind of, so we try to. So the last thing that we have done, it's also in a PhD with Julie Raconton-Very. It was to work on the adaptive facade. So with PV, double B-phase PV. Here you have PV, okay, semi-transparent PV that can convert energy on the front face, but also energy on the back face. We call that B-phase PV. It is used on big PV central when you can have direct radiation, also reflection on the back side. Okay. So for this envelope, we wanted to develop a principle of adaptive facade. So here on the skin of this facade, we have developed this kind of B-lame components. So it's two materials that have different way to dilatation with temperature. So as they are together, but one, when it's hot, try to go in this direction and the other no, it will generate a friction like this. Okay. So we develop that on the fact that here we put a reflective coating. The principle, it was the first attempt, is that during summer, the sun is higher in the sky. So we'll cross the PV or not. And here at the back face, you have an inflection of this component because the temperature is higher. Okay, so when the temperature is higher, it will move, and so it will create a kind of mini concentrator. Okay, that will reflect the radiation that go through at the backside of the PV. During winter, it is cold, so this will not move. It will be stable, okay? So it will remain on the skin of the building. It's good because the rays of the sun is lower in the sky for latitude, and so it's more horizontal and go through the PV facade. That could be reflect or absorb the radiation for the building, because the building need also energy gain. Okay, so like this, it is more close to the building skin and can keep heat to transmit to the building and reflect a part also to the PV. So it is what we try to keep on developing, so to have adaptive facades that can have functionalities that can change by themselves and can be benefit for depending of the season to the building. So it's a kind of example that we have a new PhD trying to go on this direction by also playing what I was telling you, photonics properties, so optical properties that could be also interesting depending of the angle of the radiation.
What is the material? The material what you use?
It is aluminium plus kind of polymer at the backside, a film polymer that is more rigid than aluminium. Aluminium want to move a lot with temperature. And it is
having higher thermal conductivity. Material having higher thermal conductivity.
Yes. Just maybe to finish on this, making a zoom on the PVT that I presented to you here. It is about the absorber. It's the same mind as a bio-inspiration. The absorber we have developed is a fractherm absorber in aluminium. So you can see here the flow of the water. So it is made in aluminium, and so it is a kind of leaf. The advantage of such a grid of water is that the pressure loss is limited, and the temperature was quite uniform at the surface of the heat exchanger, because at the surface of a heat exchanger we put the PV cells. Okay, so it was just the innovation about that has been tested in a control bench at Ines. So it was artificial light, artificial wind, to test this component in controlled conditions. So we found that the thermal was very good, thermal performance was very good. We were, I think we plot that, no. Compared to a classical solar thermal, it was quite comparable. We could reach temperature around 80 degrees. Electrical performance was also good. The main issue regarding this collector was to manage independently thermal and electricity, because if you want thermal, you are destroying the PV function, and if you want PV, you are not enhancing the thermal. So after we have developed a way to use it only few hours during the day for domestic hot water, and then after to prioritize the PV production. I have finished for this overview of innovative PVT, BIPVT, and I'm ready to answer some questions if you have.
The presentation is quite impressive, and I know we have learned many things, new things.
We are playing a lot. No, it's interesting.
It's interesting. If you have any questions,
sir, actually,
you can use this one.
it's okay. Right now you are working on
Yes, yes.
means you are so it's general question like you are working on PVT with different working fluids
Yes.
and you also has done research on like water, air and everything. In my case I am working on PVT with water, but means for better harnessing the solar PVT, so what you will recommend, like for PVT water or PVT air for in future?
PVT water, the main barrier is level of temperature that you can reach if you want to produce it. Because on this experience here, clearly, we had at the end a very good PVT
Yes.
collector, covered, but it was too strong for the PV function. It was good for the thermal function, but too strong for the PV function. So uncovered seems to be the best solution. But how to be able to reach more hot temperature is the question. Maybe to offer coupled to another system to upgrade the temperature and things like this. Air, I think, is not the same objective. I think air is more adapted to building needs because it's quite flexible. And now the new building are quite well designed. So I think the heat needs are less important, and we have to find also. I like a lot to play with air because yes, it's flexible to inject or to get rid of, or to mechanical, or to have natural ventilation. Maybe in the water, PVT water, it could be also a direction to find a thermosiphon system that could sometimes use a pump, sometimes use natural circulation. To have flexible PVT water could be interesting, maybe also.
Yes, sir.
And the coupling with heat pump, yes. With PVT with heat pump is a good coupling, yes. There was good experience on that.
And see, there was a discussion about this insects and then maybe butterflies. So how we are mimicking their things like the spores and it's very difficult to understand their behavior practically, and then understanding their behavior and implementing in the real.
No, yes, in reality you are right. We couldn't reach. We could never. I think we will never be able to reach a real insect or plant interface because it's too complex. All the functions are integrating in the same materials. Whereas for us, usually when we want to add some function, we add materials. To have one materials that have all the functionalities is very hard. But at least you can identify one property that seems to be interesting to develop and to enhance. Usually it's that in the whole complexity of only single materials, there is one property that could be interesting to use for our purpose. And it is what we call bio-inspiration. Then it's better, I prefer bio-inspired. We get inspiration of what we identify. That biomimic is strong. And I think we never biomimic an interface. The domain where it's more simple, it is the domain of some materials and more active, where for example, they are using some physical, geometrical, they are reproducing geometrical interface. For example, for swimming pool, there was a Speedo that has developed a swimming coat that has the same geometrical structure of the skin of a shark. And it was very efficient because when you look at the skin of the shark, there is small geometrical design that allow to generate cavitation, water cavitation. So that means that water cavitation, it is evaporation of the water become gas. That means that the shark, when he is swimming very fast, is swimming on the vapor, not on the water, because all around the skin, finally there is cavitation, so there is a small layer of vapor and not of water. So it's going very fast. It has been also implemented in the army for the missile, submarine missile. What do we call that? Torpille. That are the same process that they generate cavitation, and so they are traveling very fast. So geometry is more easy to implement, but yes. And what is difficult is also that in one material you have multifunction, but all the scale have a specific design. When you look at the nanoscale, there is a specific design that will imply a property at a microscale, and the microscale design have a property that will imply a macroscopic, so very energy consuming if you want to reproduce that. But modestly, we can at least identify one interesting property and try to, with other materials, or to generate the same property or generate the same phenomena. It's at least one innovation.
Yeah.
Yes.
Any question?
Okay, thank you, sir. Actually, I do have two questions. One is regarding that PV system with painted inks.
Which one?
PV system.
Yes.
That was painted with inks.
Ah, yes. It is.
Uh,
It is also here. You see, we have made wood, terracotta, and stone.
Yeah, my question here is, so far, we do have efficiency decrement because of dust.
Ah, yeah.
So
Yes.
when we are painting inks on PV system,
Yes.
its efficiency will decrease.
Yes.
Or else, actually now, what I'm observing is the paint is overall.
No, it's just some point. Like you see here, there is a zoom. Yeah. It's not fully painted.
Alright,
It's just
okay.
a printer that puts some dot.
All right.
And
okay.
so when you are far, it looks like uniform, but when you are close, we were playing with the distance between the dot to find a good compromise between loss of efficiency and far aesthetical aspect.
Okay. The other question is regarding building integrated PV system.
Yes.
How can we perform its maintenance, and how can you identify the faulty module or PV panel? Because different, maybe so many panels are there that are integrated with building. Maybe the building, maybe it's too big. So I do have doubt on its maintenance.
Yes, you're
stuff.
right. It's a good question. It's less easy to have access to the PV integrated than on a PV central. You're right. For roof or for facade, you are not going on your roof every day and look at the facade every day also. So we are working on the identification of problem, if there is. And so this Friday that we will speak about performance again, a tutorial. I will present you tools that we have developed with a startup. We create a startup that is able analyzing the signal of the facade or of the roof to identify if there is a good operating condition or if there is a problem. So the first point is to be able to identify that as soon as possible, because we identify that some collectivity, for example, wanted to show the example and integrate PV system, but they didn't create a service in the collectivity to look at the PV panels. So finally, they put the PV panels and nobody follow if it is operating well. They don't. And so it is important to have such kind of alert to see there is a problem, or you should clean your PV, or because the first point. And after, yes, it is the access for the facade. You're right. It is more costly to go and change PV panels in a facade than in a PV central. So the first point is to be able to identify as soon as possible when there is a problem or a decrease of the production. And it's not so, there is not so many tools that allow that. When you will put a facade or a roof, you will not put a meteorological central, put some thermocouples to follow the temperature. So it's not possible. So the tools that we are developing are analyzing the production, and depending of the production, I show you some, for example, when there is shadow, there was a drop like this, so is to make the link between phenomena and the impact on the PV central. So, and to identify, so if there is that, it is because there is a dust on the one panel. If there is that, it's because one panel is destroyed. If there is that kind of production, in between. So this is the first part, which is also part of research at that time, to be able just only on few signals to identify the problem, but also the origin of the problem. Because to identify that it is producing less, it's easy, but never done. It's never done, but it's easy to see that, no, today I should have produced more. Because there is a direct link with the meteo. So one day to another is different meteo. So you don't know if it's a good production or not. Okay? But it is a more simplest thing. But then after is to, if it is not the results, the production which is expected, is what is the origin of this discrepancy. So it's also a large field of investigation.
Maybe you can ask this online. So online participants, if you have any questions, you can raise your question.